Today we are going to talk about a research paper called Neuro-Inspired Control Architecture to enhance robot self-preservation and adaptation in autonomous navigation tasks. So what is this research paper about? So basically, robots need to have some kind of fear response, flight or fight situation like a response. So for example, if there's a obstacle which came up directly and you were inattentive, you get that instant fear response of just backing out. For example, you misinterpreted a, a rope for a snake. So what do you do is you just walk and see that rope which you misinterpreted as a snake and have a fear response, you back out. Oh, a snake. Then see and see it was actually a rope. So that's what we are doing right now. Make this fear understanding happen for robots. So these responses are called low rod responses. Low rod responses are responses where you have that instant fear, instant moment. That is called low rod responses. And higher order responses are responses where you take take time to process what actually happened. So you backed out and misinterpreted the snake as a rope. That's a higher order response. Like you saw that it was a rope, actually a rope, calculated it and realized the situation. That's a higher order response. The lower order response is when you actually misinterpreted and backed out of fear. So that's a lower order response. These responses are from the actual brain, which have been incorporated and inspired by and tried to put in this robot. So if you navigate around, if a robot navigates around obstacles or any signs of danger, this research paper has proven to make it a better alternative for obstacle navigations or dynamic obstacles which come up. The robots will have a low rod response for these kind of dangers. So instantly they move out or back out, and after that, the situation is interpreted by the high rod response. So, how did they go about all of this? This flowchart, thalamus. So, thalamus is again inspired by the brain. So, what does the thalamus do? If we compare it with the robots, thalamus is a sensor which detects what just happened. So, yep, the amygdala. What does the amygdala do again? It creates a fear factor. It shows how much of that particular thing is actually a threat. It calculates the amount of fear, processes the amount of fear. At the same time, for a robot, the fear is analyzed, it's detected through machine learning and artificial intelligence. Then it goes to the hypothalamus. Hypothalamus brainstem cerebellum and creates a motion according to that endocrine system, autonomous system, musculoskeletal system. So these kind of systems create a response according to the fear factor. If there's a threat, these things will be activated. Again, if we consider the robot architecture, this flowchart represents the robot architecture. Sensors detect it. Thalamus processes the detection. Amygdala. Amygdala sees the fear factor in it. It's a neural network here. Shows how much fear, probability of fear there is. Then the NPMC gives the motion, the reaction for this fear factor. Okay. And this then goes to the musculoskeletal system, which reacts accordingly. The robot reacts accordingly. This is what happens. This is the basic interpretation. low road architecture. So low road is basically the instant response we have, and high road architecture. High road architecture is the time we take to process what happened. Uh, there's not much mention about the high road architecture. They have not implemented it, but low road architecture has been implemented. So the thalamus processes it again. Amygdala sees the fear factor. Brainstem cerebellum connection just gives you the motion for that reaction. So accordingly for that robot, we give that reaction. How is the training of the amygdala is done? The neural network, again, which I mentioned.